This is the example from from slide 15. It says how much energy in kilojoules is required to raise 100 grams of water from 25 degrees Celsius to 120 degrees Celsius. And we're given a specific heat for water, both as a liquid and as a gas, and we're given a delta H of vaporization. All right, so the way I would look at a problem like this is I would draw the heating curve, because we know water boils at 100 degrees Celsius. At 25 degrees Celsius, that's right around room temperature. At 25 degrees Celsius, we know that water is going to be a liquid. So if you start to heat water, that energy you add, all right, that energy you're adding is going to go into increasing the temperature, increasing the kinetic energy and increasing the temperature of the water until you hit its boiling point. Then at 100 degrees Celsius, that temperature increase stops. If you keep adding energy, what happens is that energy is being used to break intermolecular forces, used to change the liquid water into a gas. Okay? Then if you keep adding energy, once it's all been changed into a gas, then the temperature of the gas will increase, and we're increasing it to 120 degrees Celsius. Okay? So you're starting off with water as a liquid, you're raising the temperature of the liquid, then you're converting the liquid into gas, got a phase change here, then you're heating the gas. All right? So if you want to heat water from 25 degrees Celsius to 120 degrees Celsius, you've got three different processes that are happening. One is heating of the liquid, one is the phase change, and one is heating of the gas. And you're going to have, if you want to get the total energy for this process, you're going to have to add up the amount of energy to heat the liquid, the amount of energy for the phase change, plus the amount of energy to heat the gas. When you get all three of those, then you're going to have the total energy for this process. All right? So we have three different things. We've got to calculate three different values for energy and add them all up. Heating the liquid and heating the gas. Calculating the amount of energy required to heat a liquid or the amount of energy required to heat a gas, that should be review from your last chapter, but I'm going to from your last semester, but I'm going to review it a little. There's basically two ways you can calculate, two formulas for this. One is specific heat times mass times change in temperature, all right? And so specific heat plus the mass of the substance plus the change in temperature tells you how much energy is required to heat it. The other option is the molar heat capacity times the number of moles times the change in temperature, okay? And both of these formulas work. The way you decide which one you want to use is based on what you're given for the information. So in this problem, we're given specific heat. Usually specific heat is abbreviated CP, although it kind of depends on the textbook. In this case, we're given specific heat. We're not given molar heat capacity. We're given specific heat. So this is the formula that we're going to use. But you'll notice specific heat is different for the liquid than for the gas. So you're going to have to treat each of these portions separately. So first, let's look at the amount of energy required to heat the liquid. Right? The amount of energy required to heat the liquid is going to be the specific heat of the liquid times the mass of the liquid times the change in temperature of the liquid. So specific heat of the liquid water, we were given it as 4.184 joules per grams times degrees Celsius. The mass of the water, we were given as 100 grams. And change in temperature. Change in temperature, all right? Anytime you have change, it's final minus initial. So it's going to be the final temperature minus the initial temperature. And a lot of people get confused with problems like this because they want to call 120 degrees the final temperature. But 120 degrees is not the final temperature of the liquid here, right? After 100 degrees Celsius, you don't have liquid water anymore. So the final temperature of the liquid water is 100 degrees Celsius. Initial temperature of the liquid water in this problem was 25 degrees Celsius. Okay? So delta T is 75 degrees Celsius. Right? So Celsius is going to cancel with Celsius, grams with grams. If you do the math here, what you should get is 31400 joules. All right? 31,400 joules. I rounded this to 3 significant figures because that 75 had 3 significant figures. So that's the amount of energy it's going to take to heat the liquid from 75 degrees to 100 degrees. Right? You can do an analogous calculation for heating the gas. All right? Specific heat of the gas times the mass times change in temperature. Specific heat of the gas we were given in the problem as 1.84 joules per grams times degrees Celsius. Mass of the gas, still 100 degrees, right? Because all of that liquid water was transformed into gaseous water. Delta T, final temperature in the gas, we were given that we're heating this to 120 degrees. Initial temperature of the gas. Initial temperature of the gas is not 25, right? Initial temperature of the gas is the first temperature at which we have a gas. That's 100 degrees Celsius. All right? So delta T ends up being 20 degrees Celsius. Your Celsius cancel, grams cancel, and this gives us 3680 joules, 3,680 joules. That's the amount of energy it takes to heat this gas. All right? So that's pretty good, right? So far now we have the amount of energy it takes to heat the gas, the amount of energy it takes to heat the liquid. Now we need to know how much energy is required to do the phase change. Right? And to get that, we're going to use the delta H of vaporization. We were given, can't see that. We were given that the delta H of vaporization for water is 40.67 kilojoules per mole. All right? What this tells us is, if we had 1 mole of water, it would require 40.67 kilojoules to turn it from a liquid to a gas. All right? But we don't have 1 mole. We actually have 100 grams. So we're going to have to convert the 100 grams into moles. We have 100 grams of water. If you go to the periodic table, oxygen's about 16 grams per mole, hydrogen's about 1.01 grams per mole. So that means molar mass of water is equal to 18.02 grams per mole. That means if we had 1 mole of water, it would weigh 18.02 grams. And we can use that as our conversion factor. Grams are going to cancel. And I got, oops, I didn't write out the intermediate value. And that'll give us moles of water, right? But I didn't stop here when I did it, all right? If you do the math right now, what you'll get is moles of water. But we don't really want moles of water, right? We want energy. But we know the delta H of vaporization tells us that 1 mole of water means you have to put in 40.67 kilojoules of energy. So you can use that as a conversion factor to convert moles into energy. So I went ahead and put moles on the bottom, so moles would cancel out. The 40.67 kilojoules, on the top. Moles cancel with moles. If you do the math now, slide in another piece of paper here. If we do the math now, what we get is 225.7 kilojoules. All right, 225 kilojoules. So grams canceled with grams, moles with moles, and all we're left with is kilojoules. So this is the amount of energy it takes to do the phase change. So now, let's slide this up a little bit. We have the amount of energy it took to heat the liquid, the amount of energy it took to heat the gas, the amount of energy it took to do the phase change. All we have to do is add these 1, 2, 3 numbers up, and we can get the total energy for this process, right? The only tricky thing to remember is when you're adding numbers, they have to have the same units, all right? So before we can add all these together, we're going to have these either in terms of joules or kilojoules, depending on what the question asks for. All right, I didn't specify. Oh, yes, this question said how much energy in kilojoules. So I'm going to go ahead and convert both of these into kilojoules, right? In every 1 kilojoule, there's 1,000 joules. So what that gives me, I'm going to write this down at the bottom here, right? Our total energy is going to be the amount of energy it takes to heat the liquid. That's 31.4 kilojoules. The amount of energy it takes to heat the gas, that's 3.68 kilojoules plus 3.68 kilojoules plus the amount of energy it took to do the phase change. All right, and when you add all these together, you should get 260.8 kilojoules. All right. A note on significant figures. All right, both of these numbers that we got for heating the liquid and heating the gas, they both had 3 significant figures because of the 3 significant figures in delta T. The amount of energy for the phase change, all of these numbers I used had 4 significant figures, so this had 4 significant figures. The rule for addition and subtraction is that you go the fewest number of places after the decimal. So this has 1 place after the decimal, this has 2, and this has 1. So when we add them all up, we report our answer to 1 place after the decimal. So that's the significance of the sig figs there. There's some example problems like these in the homework, so it'll give you some more practice. My only advice would be when you do these on the homework, I would highly recommend that you start off by drawing a diagram. I know these things seem kind of silly, but I think it really helps you to establish which phases you have, which phase changes are happening, and where the breakpoints are. Okay, so I think it's important. It doesn't have to be to scale or anything like that, but draw in a little diagram. What phase are you starting with? What temperature does that phase end? What phase do you get? What temperature does that phase end? Okay, and I think that will help you a lot on the homework problems.